Good afternoon, everyone. Welcome to today's Resilience of Autonomous Systems seminar. I'm Radu Kalinescu. I'm Professor of Computer Science at the University of York, and I'm delighted to introduce our speaker today, Dr. Robert Skilton. Rob is Head of Research at RACE, which is the UK Atomic Energy Authority's Centre for Robotics in Challenging Environments. He leads at RACE a team that specializes in robotics, autonomy, perception of operation and inspection in hazardous environments. And the focus of his team is primarily on enabling nuclear fusion energy, but they are also working in transformation of nuclear decommissioning. Rob's talk today is on remote maintenance and robotics challenges for nuclear fusion. And without further delay, I would like to invite Rob to start his presentation, and he agreed to answer questions both at the end of the talk, and if you have questions during the talk, please raise your hand and he will try to answer those as well. Whenever you want to start, Rob.
Thank you very much, Radu, and hi everyone, good afternoon. I feel like I need to introduce myself, but Radu's already done that for me, so I won't. But yeah, please feel free to ask any questions as we go. I'm happy to make this more of a discussion. As Radu mentioned, my organization is mainly concerned with the delivery of fusion as an energy source. So obviously with us as a robotics lab, that is primarily our focus, and there are lots of challenges for robotics and fusion, which I'll talk about today. I'll talk about some of today. But the second part of our organization's mission is maximizing the wider benefit. So that's about achieving impact in all sorts of other sectors where nuclear decommissioning is probably the most relevant. So I'm going to talk through some of the examples of some aspects of what we're up to. It's really just the tip of the iceberg. I tried to pick out the things that I thought were most relevant to the resilience theme. If there's anything else that people are interested in as well, please feel free to ask me questions. We'll get in contact and we can have wider discussion. There we go. Okay, so this is one person's opinion on the delivery of fusion. Lots of people believe that fusion is a really worthwhile thing to do. And for me, and for a lot of the people I work with, fusion is a brilliant thing to work on because it not only presents us with some really interesting technical challenges to solve, but also gives us a potentially viable way of solving some of the energy crisis and planetary cleanup challenges that we face today. So fusion is a low carbon energy source. It's safe, it's reliable, it's sustainable, and it's energy efficient. These are some of the great things that everyone who's interested in fusion wants to achieve. And it's definitely part of a complementary solution towards green, clean energy, but it's really difficult. So we mentioned things like 10 times hotter than the sun, 100 million degrees Celsius, next to things that are near absolute zero. We can talk about high neutron radiation fluxes and gamma radiation and things like that. We can also talk about very, very large and expensive machines and high-powered magnetic field, getting fusion working as an energy source. And that's what our organization is primarily working on. Unfortunately, that means I can have a conversation with all of you about some interesting challenges that need solving. So my motivation here is to try and explain what the challenges are to best and brightest people so that you guys can help us solve our problems for us. So this is the ultimate goal. It's a fusion power plant. And the idea is you suspend a plasma inside a nuclear fusion reactor. And the same nuclear process that occurs in stars in the sun produces vast amounts of energy from hydrogen, different isotopes of hydrogen. and it produces two main byproducts, one of which is helium. So that's the ash, that's the waste, if you like. And the other is a lot of high energy neutrons. And those neutrons are how we generate electricity to produce the energy. The big problem is that these neutrons also damage the machine. So unlike conventional power plants, we end up in a situation where the components of the machine need to be replaced on a regular basis. So what that means is frequent removal and reinstallation of components, many of which have cooling water connections, cooling pipe connections, fueling pipe connections. And so we end up with some very complex maintenance operations that need to be conducted. These typically involve access through narrow ports and the removal and replacing of large components, but also making and breaking of those cooling and other service pipe connections. So that means cutting, it means rewelding, and it means validating welds to nuclear safety standards. And in terms of fusion, robotics and maintenance is really critical. There is no way we can get to the stage where there is a commercially viable fusion power plant without having an appropriate and suitable maintenance strategy. If you can't maintain a power plant, you can't operate it, and you can't generate electricity, and you can't make money from it. If you can't maintain it efficiently enough, you will end up making a loss. So these complex systems need to be maintained regularly, but also remotely, reliably, and very efficiently. This is a picture of ITER. This is the device that's being built in the south of France. This is not a power plant. This is an experimental reactor, but it shows gives you some idea of the level of complexity associated with these types of devices. This is, I don't know, maybe 50 meters tall, something like that. It's a very, very big and complicated machine. It's probably the most complicated and expensive scientific project that's ever been built. So RACE, my organization, is set up to do this. We're set up to deliver the robotics and remote maintenance solutions that are required for delivering fusion. We were set up in 2015 in order to exploit the lessons learned from what we'd previously done in fusion. And we have this facility. It's now actually a lot bigger. It's been upgraded and extended since this photo was taken. Which houses around 300 people, 350 people working on robotics for nuclear scenarios. So the idea was to take the experience that we'd had from JET. So JET is this device here. And this is based in Culham in Oxfordshire. And if any of you want to come and visit and see what goes on down at the facility, you're more than welcome. Please get in contact and we can arrange visits. But this is a location which has this interesting and unique feature where we've gained more than 35,000 hours of robotic remote maintenance experience inside a fusion reactor, inside a nuclear context. So this is a really unique level of experience that we're looking to transform into wider benefits. That operational experience is backed up by much more experience in terms of training, process development, and mock-ups. So when we start to get into the conversation around trust and resilience, you can see that most of these operations, to get to the stage where they're even considered for being conducted in a live nuclear environment, they've gone through probably thousands of hours of training, task development, mock-up, rehearsals, and have used all sorts of digital and process tools to assist with the feature, with getting to that stage. So you can see some of the types of devices that are typically used here. This is a sort of telemanipulator robot that's illustrated in a virtual reality visualization. So there's a 3D rendering, a digital twin essentially, of what's going on inside the reactor. And that's used for planning and training, but it's also used for live remote viewing. We can see some of the sort of long reach boom robots, which are used to access in through those narrow ports and reach a long way into these environments. And we can see some of the mechanical tools and other supporting software tools that are used to support this. And there's really a lot to it. It's a complex and interesting environment. So that's operations at JET, and that has primarily had the purpose of being there to support the fusion experiment. So maintenance is being done there to support the scientific physics campaign. But we're there to understand the maintenance challenges and the robotics challenges and the AI challenges, and look at the next generation and how we can advance the state of the art, how we can do new things that help solve the challenges that are going to be faced in the future. So this includes things like the next generation of fusion projects. How do we solve the problems that are associated with these different devices? We look at things like hot cells. So this rendering here is a mock-up of a viewing mock-up. It's a visualization rendering from the first of a kind windowless hot cell in the European spallation source. So this is something that we have procured and delivered as part of the UK contribution to this amazing project, which is being built in Sweden. It should come online in the next couple of years. And it's a fully remote windowless cell for cutting up highly active waste components. We've been doing a lot with digital technologies, so you may have come across things like Cortex, which I know we've worked with a few of you on previously. But generally, we're interested in digital technologies and how they can help support this type of application in future. And then also handling tools and systems. So we looked at some of the manipulators. This is something that we have been working extensively with over the past 10 years at least. And we can see some sort of different designs and different ways of doing that, which are more and more common in some of our experiments and trials these days. And this kind of innovation, generally we do in partnership. So our default working model is to partner with others who have better expertise than we do. And RAIN is an example of that. So we partnered with a whole bunch of universities and companies around the UK and internationally to deliver innovation in robotics and AI for nuclear. So this particular project was largely aimed at decommissioning, but also had a fusion steer to it. But it gives you an idea of the sort of work that we do in order to move forward in the technology and the capabilities that are available to be able to support our mission in delivering fusion and deliver wider benefits like helping do decommissioning and nuclear cleanup safer and more cost effectively. So some quick examples of this. We can talk about remote inspections. So this is some of the work that we've done with the RAIN Hub in terms of robotic inspections inside nuclear facilities. So what we have, the three on the left here, are about mobile inspections inside a drum store. So this is an actual nuclear waste drum store, which is being autonomously inspected and mapped using mobile robotics technology. We have autonomous vehicle technology, which is being used to map and identify issues inside nuclear reactors. So this is inside the JET tokamak. This is actually a piece of work we did in collaboration with Oxbotica, the car company, as well as ORI, to deploy some of their technologies inside JET to map and detect changes from the baseline and from what was expected. And then we're also starting to use things like Spot, quadruped type robots for nuclear inspections more and more these days. They have a really important advantage, which is kind of critical in the nuclear industry, in that you can put them inside a plastic bag and still operate them. If you look at wheeled and tracked vehicles, it's impossible to do that. And what that means is where you have nuclear environments which typically contain radioactive or contaminated dust, actually you can't keep it out of the machine, which means it's very difficult to transfer and reuse or maintain that machine. When you have a machine with legs, you can put it inside a plastic suit just like you would a human being. And that means you can easily decontaminate, transfer, and reuse these types of devices, which is a real game changer in terms of nuclear facilities. One of the other aspects that we've been looking at within the RAIN Hub is remote handling. And this is taking some of the lessons learned, some of the digital technologies and telerobotics technologies, and looking at applying it to different challenges. So this is accessing again through narrow ports inside a box designed for human arms, and looking at how we can use robotic technologies for a wide range of tasks inside nuclear glove boxes. And this is really important because there have been accidents recently in nuclear facilities where people's hands have been punctured by sharp objects inside these glove boxes. And we don't want people to have to put their hands in such dangerous places. So we're investigating a whole range of robotics and AI technologies, sensing technologies, planning support tools and software to help with this challenge. And we'll talk about some of the challenges of this in a bit as well. And finally on this topic, so one of the things that we've been working heavily on that I hinted at earlier is the software architectures and how you standardize software such that it can be easily redeployed, reused, and used to support the deployment of modular, reconfigurable robotics systems into decommissioning. Now, this is something I probably should have focused a bit more on in this talk. So feel free to ask me about it and we can go into more detail. But one of the big challenges with nuclear decommissioning in particular is that historically, bespoke, large, high-cost systems have been designed and deployed for very specific, narrow tasks. And that's really difficult because when you get to decommissioning scenarios where you don't necessarily know what the situation is or what you're going to have to do the next day, what you really want is something which is very agile and versatile and can be reconfigured and redeployed for different tasks on different days. So that is something that we've been looking into the software aspects of, and it's also something which has really interesting challenges, but also opportunities from an assurance perspective, in that the safety case, the cybersecurity cases, and just any kind of assurance of the behavioral function of the system is different to how systems are usually validated. Okay, so I mentioned getting you guys to help with our problems. So one of the things that I've been thinking about and working with my colleagues on is identifying some of the top challenges for fusion remote maintenance so that I can convey these problems to other people and give people an understanding of what the top challenges are, where your research might fit in, and how you might go about that. I'm also interested in providing data sets, facilities, access to physical and virtual facilities, and access to people that support this. But this is our current list of top 10 challenges for remote maintenance in fusion. And I've already talked a bit about some of these. I think some of them are more relevant than others to this particular seminar. So I'm not going to go through all of these, but I'll make sure you have a copy of these slides. Feel free to read through this and ask me on any of these. What I'm going to do is go and talk about a few aspects of this. So I'm going to talk a bit about the environmental compatibility and the radiation issues, a bit around the deployment and recovery of systems, and then give a few more specific examples towards the end that I think will help with that. So starting with radiation, this is something I mentioned at the beginning. Radiation is a big challenge in nuclear fusion for conventional systems. So because of the fusion reaction, we end up with a process called activation happening inside the vessel components. So the steel components, the steel vacuum vessel, and the metallic wall components of the machine become more radioactive through nuclear processes. And what that means is we have a very unpleasant hostile environment. It's fundamentally the reason we can't send people in to do maintenance. You really wouldn't want to go anywhere near this. And it means it's also extremely challenging for any kind of off-the-shelf conventional robotic systems. In the worst case, typical off-the-shelf electronic devices would last seconds, if that. And there's a full spectrum through from very high radiation environments right through to human accessible environments. So this means we have to design specific systems to solve this. It means we've got a whole bunch of challenges that need to be solved to get systems in. There are strategies for this, but it also means that there is a high degree of expectation of systems to fail in some way. And failure of systems is fine. If a camera dies and you can throw it in the bin, that's not a problem. What's more of an issue is where a system fails in a way which means it can't be recovered and it prevents the machine being maintained, or it prevents the machine from being operated as a power generation asset. If you think about the long boom robots that I showed earlier, if you imagine one of those was inside the reactor, like the picture here, and it failed in a way that meant you couldn't remove it, then your £20 billion energy generation asset is suddenly useless and isn't going to make back the money that's been invested, which is obviously a major problem. It's not necessarily going to cause any hazard to people, but it's just not the right solution. It won't do the job that we need. For electronics, it's bad for polymers, which are also affected, and it means we need to do a lot to overcome. So in terms of radiation hardening, we're not at the level where the radiation generally affects the structural elements. But in terms of robots, the typical types of things we're talking about are things like communications, sensors, power supplies, actuators, and processing units. And these are the types of devices where a robot is primarily, in some ways, made up of these things. And in designing for this type of environment, the radiation impact on these devices, on these types of functional units, needs to be strongly considered. So there are lots of ways of doing that, and the general process in the nuclear industry is doing as is stated on the top left here. So the way of radiation hardening a component in a robot is, first you look at elimination. Can you do without this component? Do you actually even need it in the first place? If you can get away from the component, get rid of the component, you not only solve the radiation hardening issue, but you potentially solve some complexity issues, make the system simpler. Can you replace the component with something that does the same function that is more tolerant to the radiation environment? So there are some examples down the bottom left. For example, we have optical encoders, which are typically digital components. They have semiconductor elements within them. They have glasses and optical components within them. If we can substitute them for passive analog electrical components like resolvers and potentiometers, that potentially solves the problem. The third way is by separation. So what this means is, instead of doing the processing on board the robot? Can we do the processing 200 meters away in a safe environment? And that is actually probably the most common way currently used in radiation hardening of robotic systems. What that means is we can take all of the sensitive components and put them in a safe area, but it also means we have many, many wires, and wires cause major problems. Wires cause major problems in terms of electrical and signal noise, in terms of the mechanical properties being very heavy, bulky, and stiff. And sometimes it's just not feasible to even find the space to put the wires in to do this. The fourth option is shielding. In high gamma environments, this typically means putting large thicknesses of lead around the components. And that's something that's usually not possible because of the mass and the space required to do that. And then the final option is radiation hardening by design. So this is something that we're working with a number of companies on, developing components, for example, polymers, optics, and semiconductors that are simply more tolerant to radiation and are able to operate for reasonably long periods of time in that environment. And that's very expensive and very difficult to do, and it takes decades. It's a long, slow process. But nevertheless, that is something that we see as necessary to some degree and is part of our strategy. So in terms of dependability, clearly these systems need to be highly dependable, not just for safety reasons, but also for productivity and commercial reasons. There is often no possibility of human access in the event of problems, which means we need high reliability in all of these systems. There is usually redundancy. So if one system fails, we can roll over to a second redundant system. There are always recovery strategies. If a system fails, there needs to be a viable plan to recover the system such that it's not blocking the environment or preventing other activities from happening. Some scenarios that is really difficult or not possible, in which case the fallback option there is rescue. So what that means is having additional equipment to go in and rescue the failed system. And on top of that, further than conventional robotics, we end up with increased levels of safety requirements and increased levels of security requirements. So what this means is that overall, we don't just have to design a system to do a particular job. We have to build in all of these additional requirements, and that adds orders of magnitude of additional complexity and cost to the delivery of these types of systems. This is generally, again, applied in a sort of hierarchy. So for frequent failures, you would typically deploy more things like more redundant systems and high reliability. For more infrequent failures, you might tolerate the need to recover the system using backup systems. And for extremely unlikely failures, you might not have any option other than to design rescue systems to go in and remove the system. Okay, so I'm going to talk through a couple of examples of those types of things to try and make these vaguely abstract concepts a little bit more concrete. So these are examples from the JET remote maintenance systems again. So for example, we have motors on robot joints. Typically, there are more than one, and they will be independently wired. So there will be redundant wiring as well as with redundant motors. In terms of position sensors, you will see primarily resolvers and then secondary potentiometers. So we've got redundancy and diversity here to eliminate common mode failures, but also to alleviate some of the wiring restrictions. With tachometers, so these are all pretty old-fashioned devices that aren't really used very much anymore. They're they're used because of their tolerance, and they're typically analog devices that don't fail too badly in radiation environments. So there'll be redundancy to per actuator, and they'll be independently wired. And then there'll also be spare wiring, which can be used if necessary. Here are some examples. So what we've got here is the cable looms coming through the joint in a long reach boom. What you can see here is a motor with a tachometer. There's another motor with a tachometer behind it. They are connected into two independent gearboxes. So this is redundant gearboxes as well to eliminate the possibility of seizure. And that's joined into a coupling which can be remotely disconnected, which is one of the recovery scenarios. And that's what this slide shows. This is a slightly different actuator design. There is a joint which has a additional motor, which is primarily there just for the purpose of mechanically disconnecting the joint, so that if a motor fails or if the gearbox seizes, the actual joint itself can be disconnected, leaving it just on the bearings, which means it will hang freely and can be dragged out. So that's the type of recovery scenario that we're talking about. In terms of rescue, as I said, this gets to the next level of complexity. What we have here is two of these telemanipulator robots. They're called mascots. One has failed. This is inside a mock-up of JET. And the second system has been sent in to do some disconnection of mechanical parts such that the other system can be removed and dragged out. We have interesting failure modes, things like if a gripper is to fail, you obviously don't want to drop anything. But if the thing that you're holding is connected to a wall, you absolutely want to drop it so you can get out. You end up with some paradoxical scenarios where actually rescue is the only option. This is very complex. It's a very abnormal and off-normal scenario, but it is one that needs to be planned for in the case that it may occur. Okay, so there's some examples with some of the existing systems that have been operating at JET for the last couple of decades. I'm going to talk about some of the things we're working on now and where resilience and trust really are important. So we have, first example of three is inspection. Got some examples here of inspection inside a facility that's probably being decommissioned, inspection inside a tokamak looking for abnormal conditions, maybe splattering of beryllium or tungsten on a tile, aerial inspection inside nuclear facilities, and in-pipe inspection, which will be geared towards inspecting the quality of the weld. So generally speaking, these types of inspections might be looking for things like contamination measurements. So that could be swabbing, or it could be passing a sensor over something. It could be inspecting a weld inside a pipe or inside a vacuum vessel. It could be autonomous robotic mobile inspection. These inspections may be being done because they need to be done for a regulatory reason. So in some cases, these types of inspection need to satisfy the needs of regulators, which means the quality and process needs some level of guarantee associated with it. It may also be done for a productivity and commercial reasons. So one of the key reasons for doing this type of inspection may simply be to prevent the unnecessary outage of an energy generation asset. You want to maximize the availability for energy and, of course, for science, if that's what the device is doing. And there are safety and security aspects to it. You may be inspecting for the reasons of guaranteeing elements of safety. You may be inspecting for reasons of security. So this is one I talked about earlier. This is an example of remote inspection, and the specific example is inspecting a drum store. So the task here is to autonomously traverse a storage facility using a mobile robot in a safe way that allows you to measure the geometry using LiDAR of the environment, detect the presence and absence and changes to the configuration of fuel storage drums, and then typically look for things like changes to the shape of the drum, or the presence of any additional corrosion or unusual features of the drum. So this is something that you are probably doing more for safety and regulatory reasons. This is the type of inspection that is currently very much done just by humans, which means people have to go into these relatively dangerous environments and do inspections, which can be time consuming. People can be very prone to errors, and is otherwise, quite problematic. So the vision is pretty obvious. I think you want these robots to be running routine, daily, hourly, monthly, whatever the frequency is, inspections, and the whole process to be automated with some level of guarantees associated with it and what you're trying to measure. Okay. The second example I'm going to come back to is the glove box scenario. So we've talked about handling. I have one of our colleagues from TEPCO handling some robot devices here. When we're talking about handling, there are lots of challenges associated with it. We need reliability in grasping. When you pick something up, how do you guarantee that you're not going to drop it? How do you guarantee that you're not going to crush it or do some damage to it? And how do you, when, for example, grasping something, how do you guarantee that it's not a dangerous object, that it's not sharp when, in fact, it shouldn't be? So hazard avoidance is a really important thing. Collision prevention is another. So often we're operating in confined spaces and have to deal with fragile components. Some of those fragile components are glass walls, which form the contamination boundary to human accessible areas. So actually preventing collisions with, say, the elbow of a robot is really important. That should be grasped. So this is what I mentioned earlier. So there is this grasp failure predicament. You need to be able to drop, you need to be able to not drop something in the event of a failure. But you also need to be able to move away. So there is this fail safe versus fail recoverable predicament which needs to be overcome. These are off-the-shelf manipulators designed for a nuclear environment. We're also operating with off-the-shelf industrial robots and seeing how they operate within that kind of environment, as well as virtual environments. And this is JET. So I mentioned glove boxes. The specific example here, Sellafield have a number of glove boxes. Every time I have the conversation, it's a slightly different number, somewhere between 400 and 650 glove boxes, which are in various different conditions, and many of which are at the end of their operational life. They're no longer used for their intended purposes. So the task with those is to clean out the contents, decontaminate them, and then move them to the stage where they can be cut up and disposed of as waste. That is something which, as much as possible, we want to enable to be done with robotics and with autonomy. But it's really difficult because we don't necessarily have access to the inside to install cameras or other sensors or devices. We don't necessarily know what the contents are. We have to access through these narrow ports. There's typically, this is one where you can actually see through the windows, which is somewhat unusual. Actually, a lot of the windows have become brown, so to the degree where you can't actually see what's present inside. There is also a process where a lot of the windows have become embrittled. So actually an accidental contact between the robot and the window could be disastrous. I mentioned puncture wounds. So typically the robots will be in their own gloves, in plastic sleeves to prevent contamination spreading. And we need to have a high degree of confidence that there is no risk of penetrating that confinement boundary. So the detection of sharp objects, the detection of pinch hazards and those types of hazards is something which is really important, and something which we need to have a high degree of trust and reliability in to be able to have confidence in doing these types of tasks safely. Okay, the final example I'm going to give is digital tools, which is a really broad category, actually, but it's kind of the third aspect of what we do, and it covers all manner of things from strategic planning tools to capture procedures and plans, tools for training, so mock-up scenarios, virtual reality environments, and simulations for training. Operations and decision support systems. So we, for example, use VR visualizations live during operations to provide additional viewing than that of the cameras, and also live remote camera viewing. So there's a whole spectrum of digital tools which are both used in operation, but also being investigated for future benefits. And one of the big areas that we're doing this is working together with guys at TEPCO for supporting decommissioning of Fukushima Daiichi. In all of these, there needs to be a high degree of trust and reliability. So we need to be able to guarantee that the training scenarios are reasonably representative and generalizable to the real scenarios. We need some level of confidence that the information present in a tool for making a plan is going to be valid for actually generating a valid plan. And operators during live operations need to have good confidence that the information that's being provided to them by these digital systems is trustworthy and is good for making, for supporting decision making. And remember, these are decisions that are being made in the context of cleaning up nuclear materials, and there are some really potentially high consequence scenarios. Here's an example. This is a piece of work we've been doing with the University of Manchester and the Korean Atomic Energy Research Institute. The task here, this is really very much at the low TRL research end of the spectrum. The task is to combine multiple sensor data from multiple sensors in a remote environment to give a real-time 3D reconstruction of that remote environment over the internet. So the place we want to be is where we can reconstruct the environment in 3D remotely over a long distance, such that someone can operate a robot and do some decommissioning tasks, perhaps from a different country. We're fusing data from multiple sensors, but also using a wide range of algorithms to selectively downsample the data in an intelligent way such that it can fit the bandwidth requirements of being transmitted over a potentially unknown connection. So this obviously has parallels with things like telesurgery and other things, but it gives you an idea of the sort of digital information representation that we're dealing with, where a high degree of trust and reliability needs to be developed. Okay, well that's all for the technical content. I'm going to just mention briefly how we operate and give some general updates. before we go into any questions. So this is just some general stuff. Hopefully that was useful and interesting and gave you some ideas and a flavor of what we're doing. We prefer collaboration. So everything we do, we want to work with the best people in the field doing those things so that we can help enable research to have maximum impact, but also help to attract people to work on our problems. We are very interested in hosting research platforms and putting platforms and technologies available to support research and to make it easy. We want to make fusion challenges attractive and accessible. We need to align our program as much as possible with other areas to maximize the benefits. We want to act as a hub to connect people. And obviously, we want to be useful and work to remove blockages to progress. So 2 general updates. One is that within the Long Ops program, this is a £12 million program, we currently have open calls for participation. So there are definitely opportunities to get involved here. There is a £1.5 million pot here that can be applied through the SBRI competition. So if you search for SBRI Long Ops or digital technologies, you can find this. There's a link here that I'll share as well. And that's in a number of different areas. On top of this, there are also procurements available, which are open to everyone. I'm pretty sure I had a slide on Taros as well. Never mind. So get in contact. I'm here. Feel free to come and talk with me at any point. We are organizing another standardized workshop on software architectures, which Anna has been very involved in the past. So that will be happening later this year. And we're also hosting Taros later this year. So that's the UK's longest running and largest robotics conference. It will be at RACE in September 2022. Please submit papers and come and join us. That's all from me, and thanks for the opportunity for talking. I hope it was interesting and useful. I'll take any questions.
Thank you very much, Rob. This was a very interesting talk. So we have roughly 10-15 minutes for questions. Anna?
Thank you, Rad. Thank you very much, Rob, for the usual very nice talk. Rob, as you know, I'm very interested in Cortex, and I wanted you to give your view of how Cortex addresses all these challenges. Why have you developed Cortex, and in the context of all these challenges that you are facing, please?
Okay, so for those of you who maybe don't know what Cortex is, I'll just briefly explain. So Cortex is a software framework that we've developed, and it was really there to solve a few problems simultaneously. The primary problem it was trying to solve is this challenge of putting together robotic facilities, robotic capabilities that can be flexibly modified in a way that is highly cost effective. So we want to be able to very rapidly reconfigure robotic systems, add functionality, remove functionality, reconfigure functionality in a cost-effective way that is transparent to the operator. It minimizes training needs. It minimizes cost of additional verification and validation, and all of those good things. It was actually inspired by a similar initiative that was done through the UK Ministry of Defence called the GVA, the Generic Vehicle Architecture. What it looks like is a software framework. It's a communications architecture and a data representation that allows for a high degree of modularity and a high degree of plug and play functionality. So the idea is these modules can be connected to each other, and without prior knowledge of each other, they are able to understand the functionality available and how to operate, how to interoperate with those systems. We've published a chapter in Anna's book, which details this in much more detail if those of you who are interested want to go and find it. It's moving forward, and I think the opportunities really are pretty endless. So in terms of the interest of the architecture, the modular nature, I think, lends itself really well to an interesting way of modular approaches to safety case, modular approaches to assurance and cybersecurity. And those are all kind of speculations. I'd be very welcome to hear if any of you have interest in expanding any of the work you're doing towards modular approaches to resilience, to assurance, and anything that would fit there. We can make Cortex available. We're planning on eventually open sourcing it, and it's there. It's a software framework which is for robotics in nuclear.
So you don't see it as being specific to the nuclear industry. It's a more general framework than that. Am I right to make this conclusion?
Yeah, it's actually, I mean, it's not even specific to robotics. It's a general purpose communications architecture that allows a high degree of plug and play functionality.
Okay.
It could be used in a wide range of areas. I think the reconfigurable aspect is something where the obvious impact is in the nuclear industry.
Okay. I guess a naval question to ask is, why not use ROS then?
Yeah, so the answer is ROS makes a lot of sense in a lot of environments. We use ROS for a lot of what we're doing. The key difference is that when you're doing highly validated systems which need to be reconfigured, this is a system that allows doing that, and it has a very different, almost polar opposite communications strategy to ROS that essentially allows self-description and allows a high degree of plug and play operation. That's really the main difference. Other than that, they're very similar architectures.
Thank you.
Colin.
Thanks, Rob. Really, really interesting. I've got a couple of questions. Maybe I'll just start with one and see what others want to say. But I wonder if you could give us a bit more information on, you said about decision support, the ideas about decision support. I wonder if you could give me a feeling for what type of decisions you're talking about when you say decision support, and what kind of information is being fed in to support those decisions.
Okay, so I'll give you two examples, because there is sort of what's being done today and sort of where we're going for the future. What's being done today, there are a number of tools which are used which give procedural flowchart based systems presented in digital interfaces to operators, such that they can make intelligent decisions about what to do given a particular scenario. So you don't want a nuclear decommissioning operation to be completely procedural, because what that means is as soon as you get to a unknown or something which is unexpected, the operation stops and needs to be replanned. So typically it's that sort of thing. It's you go to a bolt, try to undo it, and the bolt is seized. So the decision is, what do you do? So currently that's very procedural, and there are pretty well-established procedural systems and techniques for doing that. What we're looking at more into the future is more highly unknown environments. So we're looking at environments like some of the reactors in Fukushima Daiichi, where there has been a tsunami, an earthquake, a hydrogen explosion, and a nuclear meltdown, and then had hundreds of tons of seawater and sand dumped into it. And you can imagine what the internals of something like that looks like. It's a really unknown, really unpleasant, harsh environment. What we're looking at there is, at the moment, currently more on the strategic side of things. So it's about, after you can get a limited number of sensors in, a limited range of views, you can gather some level of geometric data, some level of visual camera data, some level of radiological data. And then the question for that is, what is the plan that makes most sense? So from the starting point, you have a sort of strategic planning and then operational planning support side to it. But then as you start to get into operations, you're very much in that same scenario as before, where you've discovered things are actually not exactly as you expected. All of this data you have in a model which all has levels of uncertainty associated with it. So you need to be able to both plan and then react to operational discoveries during live operations. So they're the sorts of decisions we're talking about.
Thank you.
Thank you, Colin. So the next question comes from Poonam.
Hello, hi, Arup. Thank you so much for your wonderful presentation. It was good to hear that kind of environment, because I've never been in that kind of environment. It's very hard to kind of perceive how it looks like from the distance. My research, but I particularly work on different kind of sensors and sensor-based environment in harsh conditions, particularly looking on a communication part. So I was just wondering what kind of communication channels you have inside your that kind of environment, what kind of technologies are working, and how you say these wired or wireless technologies work in those kind of environments.
Well, wireless technologies would be amazing. That's sort of the dream for us. For the very basic sensors, we typically operate on analog sensors where we have kind of high strength analog signals going down long cables. Perhaps a bit more interestingly, there is a program looking at rad-hard field bus connections. So we're talking about things like BISS and possibly things like EtherCAT, but I don't think that's quite there yet, with some degree of radiation hardness. So where we don't have so much radiation issues, we're talking about things like Ethernet and EtherCAT as standard connectivity. But yeah, that's not the case. Mostly analog wired connections, and in some degrees, very kind of simplistic field bus connections.
Okay, so is it in the future, it's a plan to move towards some of the wireless things?
Yeah, I mean,
still going to stick with the same wire?
So fundamentally, one of our biggest problems is wires. I know it sounds kind of trivial, but wires are a nightmare for nuclear robotics. Field bus connections mean instead of 1,000 wires, we need 6 wires. So that's a really great place to go. Actually, wireless connections may make more sense in a way than looking at field bus connections, in that there may be sensible ways to radiation harden wireless connections and get the data through. That mean we eliminate both constraints simultaneously. So I would be very keen on looking into any kind of wireless technologies. Just for information, one of the things that's been just sort of casually mentioned in the office is using very simple analog wireless communications for things like driving motors remotely. So you know, some really basic techniques would actually, if they could be deployed in this sort of scenario, could potentially have a major impact.
Yeah, I would be really interested to know what kind of environment there is and what kind of frequencies we could deploy in that kind of environment, because I work on different harsh environments underwater, or, you know, wet soil and all those kind of things. And we were working out what kind of a communication technology or radiation can pass through. So it would be interesting. Maybe I'll connect later directly.
Yeah, that would be great. And you're more than welcome to visit. As it happens, I didn't mention actually, this Friday now, we're kicking off a new research program, 5-year program that actually includes radiation hard systems, radiation hard sensing and communications as one of the topics. So it's a really good timing to start a discussion on that.
Thank you.
Thank you very much, everyone. I see we are past 4 p.m. One final question then, Colin? Yeah, you are muted, Colin.
Yeah, it's maybe something that is very obvious from what you were talking about earlier, but I'm interested in the handling of unusual objects.
Mm.
And I wonder if you do anything, again, it's about the decision support, I suppose, to an extent. But if you know where you are in the reactor and you know the type of component that you're looking to work with, and possibly from vision or whatever the state of it, is there anything you can do about putting constraints and properties on the handling at that point? So i.e., we know that this particular component shouldn't be experiencing forces above X, and therefore, or it should be approached with a particular gripper at a particular angle. Is there anything you're doing, a kind of like putting a fly-by-wire on the handling? Is that feasible?
Yeah, it's feasible. It's a lot of that is done already. So even in the jet systems, there are constraints on positions, on grasp forces, all of those types of things. Moving into the glove box scenario, there were some really interesting challenges around the redundancy of the kinematics and the collision avoidance. We're looking at things like dynamic keep out zones and things like that to avoid collisions with moving objects, those types of things. You mentioned the handling of difficult objects. Actually, one of the interesting aspects there that we're looking at is handling of irregular shaped objects.
Mm-hmm.
And that can be quite challenging. Actually, one of the approaches we've got there is we're looking at a lot of deep learning based systems for handling, and actually the adversarial generation of difficult objects which are difficult to grasp is something that's quite interesting and has worked really well. That obviously has lots of again, assurance and validation challenges associated with it. Yeah, there's a whole range of possibilities there in terms of and in terms of operator support techniques, sort of shared autonomy, sliding autonomy type things. There is a lot that could be done. What has been done is limited more by the available time and money to do it more than the possibility of the technology, I think. So if we can get the technology much further, I think there's possibilities to take some big leaps.
Yeah, it sounds like a lot of the really interesting problems are making us throw away some of the techniques that we've relied on for a long time, right, and think creatively.
Yeah.
Yeah, thank you.
Right, so thank you very much. I think that this is all we had time for today, but thank you again, Rob, for this very interesting seminar on the challenges associated with the use of robotics in nuclear fusion, and for inviting the attendees to consider possible collaborations. This is a very hard problem. And
Thank you for inviting me. It was really nice to talk to you guys.